possible to work out the rate law for a given reaction if you have a certain set of experimental data to work with. Rate laws have the following form, and you just add more terms depending on how many reactants you have. If you have one reactant, there's only one term with an exponent. If you have 5 terms, there are 5 terms with an exponent. So if we want to find the rate law for this reaction, we know that the rate law is going to have the following form. In order to fully write this rate law, all we need now are the values for x and for y. And the way we can find x and y is by using the experimental data on the left-hand side. The exponents, in this case x and y, represent the orders of reaction. And orders of reaction dictate how much the rate depends on the concentration of each reaction. To find these, what we need to do is we need to isolate the effects of a single reactant on the rate. And we can do this by running multiple experiments where we vary the concentrations of the reactants and we see what effect that has on the initial rate of reaction. And to isolate the effect of a single reactant, what we do is we run experiments where we vary the concentration of one reactant while holding the other reactant concentration constant. And then we hold the other reactant concentration constant and vary the initial one. In this example, experiment 1 and 2 show the effect of varying the nitrogen monoxide concentration while holding the H2 concentration constant. Experiments number 2 and 3 hold the nitrogen monoxide concentration constant and vary the H2 concentration. So they'll let us find y. What we need to do first is we need to set up expressions relating the different experiments to one another. We'll look at finding the x value first, so we'll be interested in experiments 1 and 2. In this case, I've included little subscript 2's on the concentration terms, just so that we know that these are the concentrations for experiment 2. For the second expression, the subscript 1's just indicate experiment number 1. It's important to note that for experiments 2 and 1, the H2 concentration remains the same, 0.002 molar, which means that it doesn't matter what value y has, 0.002 raised to the same exponent is the same value. So these terms have the exact same effect on the rate. What we can do is we can set up ratios for experiment 2 to experiment 1, and we can actually cancel out the effect of the H2. We know that the H2 concentrations are the same. The order y is going to be the same for both experiments, so that term will cancel. K is a constant. It should be the same for both experiments. K cancels. Now we have something that looks much more easy to solve. We can actually simplify this a bit further. And now we can plug some values in. At this point, we could simply finish and say 2 to the x equals 4, so x has to equal 2, but sometimes you won't get numbers that are quite as clean. So now I'll show you a way to find x even when your numbers are not quite as easy to work with. If you take the log of both sides, you can isolate the x. And we've determined that x equals 2. Finding the second order of reaction, y, is done exactly the same way, but using, in this case, experiments 3 and 2, because they hold the nitrogen monoxide concentration constant and vary the H2 concentration. And again, the K's are constant, so they cancel, and in this case, the NO concentrations are constant, so they will cancel. And y here is obviously 1, but we'll calculate it using that logarithmic method that was shown earlier. Now that we have our two exponents, we can write our rate law. When the exponent is 1, you don't need to show it, it's implied. At this point, it's important to note that you have to determine orders of reactions experimentally, like we've just done. You can't simply use the coefficients from the balanced chemical equation and say, if NO has a 2 in front of it, my exponent has to be 2. In this case, that's true, but when you look at the exponent for the hydrogen, it doesn't match with the coefficient. If it did, it should be a 2. So you have to determine things experimentally. In a certain very special set of conditions, you can use the stoichiometric coefficients to work out the exponents. If you have something called an elementary reaction, then you can use the balanced chemical equation to work out your exponents.